We have been planning this for some times, and there is so much that we want to share with all of you. So I'm Angelo Corsaro. As you probably know, I'm the CEO and CTO of Zeta Scale, and I have the honor of opening this Taming the Dragon webinar series. But without further ado, let's get into the live of the webinar. Okay, so in terms of logistics, the webinar series is composed by 6 episodes. And we are starting today with the Zenogenesis, in which I will try to give you an understanding of why we designed Zenoh, which were the challenges that we were trying to solve. And likewise, introduce the key concept that Zenoh provides and why we designed it as such. Next week, because we will have 1 episode per week, Luca Cominardi will be getting us through getting started in Zenoh. So he will go into the very details of the Zenoh API and how actually to write application in a very idiomatic way. And you will enjoy examples in Rust, Python, and so on and so forth. Then Julian Enoch will show us how you can use Zenoh to have super simple robot-to-anything communication in ROS2, and actually, thanks to some new connector that Julian will probably demonstrate, also with ROS, so the version of ROS that precedes ROS2. Carlos, on December 13, will take us through how to use Zenoh on microcontroller and low-power networks. And here we really mean very constrained devices. Julian, on December the 20th, will be back again on stage, showing us how easy it is to integrate databases or other messaging protocol in the Zenoh ecosystem, and then how you can leverage those integration, as we will see, to deal with legacy system that are using perhaps MQTT or DDS, as in the case of ROS, or perhaps to have geo-distributed databases, as we will see to some extent in this session, and then eventually back with Julian. Then we will go off, and I guess you'll take also some time for Christmas and the New Year, and we'll be back on January 6th with Zenoh Flow. Zenoh Flow is a pretty cool data flow programming framework for Zenoh. How can you use this? Well, there are several different ways of using this. Some of our users are actually leveraging Zenoh Flow as the data flow programming framework for dealing with the swarming of robots. Other users are just using it as a programming abstraction for data-intensive application. But in any case, Gabriele and Julien Laudet will get into the world of Zenoh Flow. All episodes go live on the day of the webinar twice, at 10 a.m. CET, like today, and 6 p.m. CET. And we do that just to make sure that, depending on where you are on the globe, we can make sure that you can have a live session at a decent time. Okay, done with logistics. Let's move to a super quick intro of Zeta Scale. Zeta Scale is a new kid around the block. By the way, we unveiled Zeta Scale essentially last June, and we've been growing crazily. And what is our mission at Zeta Scale? Well, the mission is very simple. And our mission is that to bring every connected human and machine the unconstrained freedom to communicate, compute, and store anywhere, at any scale, efficiently and securely. Where efficiently means, data efficiently, little bandwidth, and efficiently in energy, which again, it's something that if you followed us, we've done quite a few analyses on the energy impact of communication, and now also Zenoh can help on that. Other things that I care a lot, for those of you that are familiar with Zettlers, we tend to be one of a kind, okay? And the selection in our team is always very careful, because besides the technical skills, which are very, very important, we care about the human, right? And we really embrace the 7 virtues of knights, okay? Courage, justice, mercy, generosity, faith, nobility, and hope. And the people that interact with us, I hope in the community, and then those that have a chance to undertake a challenging and complex project with us, actually can relate to these values. So our teams has over 10 years of experience running software companies or BU, very strong technological leadership. More than 50% of our engineers have a PhD, And as of today, we are 50 shiny Zettlers and growing quickly. By the way, we have tons of openings. So if you love what we do, just reach out because we are looking for for great talent and great people to join our team. Last slide that I want to have on ZettaScale is that again, we have quite a few of our technical staff that are well-recognized subject matter and world expert in their domain. As an example, one of the technologies that we have worked in the past was DDS. Some of you know that perhaps I was one of the guys that started the DDS standardization group back in 2003. And Cyclone DDS is our newest DDS implementation, because we had another one, but here we restarted from scratch, trying to capitalize the experience that we have had over the past 20 years. And above all, we are the inventor of Zenoh, which, as we will discover, is actually the most powerful and efficient protocol yet, and we'll try to understand why. I think it's important to share this information, because I will be pointing out weakness on protocols, certain protocols. And some of those weaknesses, as we will see, are not weakness because the protocol wasn't necessarily badly designed. Some protocols sometimes are badly designed, but most of the time, the point is, when you design that protocol, you had a specific application domain in your mind. And it was perhaps 20 years ago, and the world 20 years ago and the world today is quite different. And so things change, and protocols also have to evolve. And I think we have always been very open with respect to, with our users and people that ask us, telling very openly, yeah, this works very well in this domain, but just forget about using in this other context. And I think that this is something that does characterize us, because what we care is really innovating, building the best possible technology, and as a consequence, giving our user the best tool to solving their problem. Because we love communication technology, we love protocols, but you typically use this building block, which I consider like a nervous system, right, to build some logic in your business domain or application domain, and should have the right abstraction in order to make your life as simple as possible. And this is what we do. So this is a very good premises to the Zenoh genesis. And I would like to start with some historical background. So let's go back to the days of IoT and IIoT. So we were involved in building some of the earliest IoT and IIoT. And by the way, IoT stands for Internet of Things, and IIoT stands for Industrial Internet of Things. What is the canonical difference? Well, is that usually IoT is mostly about consumer application, or application where you don't have criticality, a connected watch, a connected home device like a connected thermostat, and so on and so forth. While industrial IoT is more about mission or business critical IoT application, where you would have connected robotics, connected medical devices, and so on and so forth. So in 2008, we were involved in one of the earliest smart city projects in Nice, that was the Connected Boulevard. Back then, we were working with Cisco and some other partners. Obviously, it wasn't ZettaScale, but it was our team, right? For those of you that are not aware, we were deeply involved also with the smart project in Singapore on the Smart Nation. And in 2014, for instance, we were part of the team, once again, with Cisco, Schneider, and a bunch of other companies that created in Barcelona the first reference platform for managing the Barcelona city, okay? So in a way, we were there. We were trying to build this system. The reality is that it was laborious. You had to stitch together so many technologies to ensure that you could have some end-to-end data flow. Why? Because all of a sudden, we were moving from systems that either were isolated in the periphery. Think about an industrial plant, or if you think about an air traffic control management system. This is a well-defined system where you have reliable network, high bandwidth network, relatively symmetric, and I would argue that that's roughly a closed system and rather homogenic. But now, with the IoT, the Industrial Internet of Things, and for computing, we had this system that's from time to time they are called mission critical or OT system that had to interact and be integrated with other systems that were more IT centric or perhaps adopting cloud technologies. And so we were finding ourselves having our application or our infrastructure that had to span potentially from a data center, public or private, and sometimes down to a microcontroller. And the issue was how do we make it work? Because there wasn't really a technology that could span across the spectrum, okay? And as a consequence, you had to build a system as a collection of putting together jigsaw by stitching and duct taping. And things were even worse when, besides wanting to deal with data in motion, right, so moving data around, you had to deal with data at rest, so storages. In such a system, where do you store the data? If you have a need of maintaining storage distributed for some scalability or minimizing the latency for accessing the data, then how on earth do you find out where the data is? So things were rather complicated. And let me try to articulate the limitation that we were finding, right? So let's take as an example MQTT, because you could say, well, you could solve this problem with MQTT. But then what was the problem? Well, in spite of the fact of MQTT being popularized as an IoT protocol, right, this protocol supports just one, let's say, communication architecture, which is the client to broker. So you can have pub and sub, whose communication is mediated by a broker, and MQTT, the basic protocol, only works on TCP/IP, okay? So already the fact that MQTT relies on TCP/IP makes it undesirable for running on low-power networks because the overhead is way too high. And in fact, many of you probably know that for low-power networks, there is a variation of MQTT, which is called MQTT SN, sensor network. And the two protocols are completely different, not even interoperable. You have to bridge between the two. There were other problems, right? Imagine, as we have this hub and spokes architecture, imagine that I have application on the edge of my system that need to exchange data in a time-sensitive manner. All of a sudden, they cannot communicate peer-to-peer. They have to go through this broker. And where do I deploy this broker? Well, usually this broker is on the cloud. So this architectural pattern was working for some application, mostly IoT, but as soon as you try to move to applications that have more stringent performance requirement or the necessity for locality, it gets a mess. And the other challenge was we had devices that would slip, okay? Some device deployed, for instance, in Barcelona, throughout the city, they would have a duty cycle. And if a device has a duty cycle, I cannot push to a device. So with MQTT, if I'm sleeping and someone is publishing data, how do I do? How do I recover the data, right? So this was one of the challenges that there was with MQTT. It worked very well for a specific scenario, right, for some class of application, but as soon as you try to go outside of that use case, things get pretty complicated. But let's take an example on the other end of the spectrum. Let's look at DDS. So DDS, I can tell you because I was part of the team that designed it, was really designed originally for aerospace and defense applications. These were real-time applications running on a fixed network where you were assuming that you had multicast, IP multicast, and you were assuming that the probability of packet loss was very, very low for two main reasons. Number one, that the network is a quality network, and number two, because systems were properly dimensioned. Why do I say that? Because if you look into the reasons for packet loss, most of the time, unless you are out in space, okay, and that's a different story. But if you are on planet Earth and you are not looking into a satellite or something else traveling across the space where there are lots of cosmic noises, but if you are on planet Earth with a wire network, okay, using an IP stack, the reason for losing a packet usually is that somewhere there is some overload situation. So either you are overloading a host or you are overloading a switch. So if your system is properly dimensioned, the probability of loss is very low. And all of a sudden, the way in which DDS setups and does its communication becomes quite effective for those systems that can assume that you have multicast, and in which predominantly the data produced by data writer is interesting to almost all consumer. Okay, so again, it was developed for this kind of systems where you really need low latency peer-to-peer communication, but it doesn't work off the shelf over the internet. Okay, it doesn't scale easily over the internet unless you break its semantics. Okay, and we've discussed this more than 10 years ago. For those of you interested, we can send material that is 10 years old that explains what are the problems in the protocol that make it non-scalable and the problem in the discovery. It has a steep learning curve, and once again, it's only push. So I still have problems with respect to the device that undergo a duty cycle. And as the stack was not intended for microcontroller, again, was intended for workstation, I mean, it's tricky to have something that is embedded and still, again, retain exactly the same semantics. Okay, so here we have two examples of technology that there were back then, one which is great for communicating efficiently on the edge, one which is very good for having, edge to cloud, but what if we need the combination of the two? We are kind of stuck, okay, and we have to go and stitch technology together. Let's take another example that was very, and still is very popular on the IT and cloud world, which is Kafka. So if you look at Kafka, great technology, but this is really designed for the data center, right? It's pretty heavyweight. I mean, you have to deploy a set of brokers somewhere in a data center, and this is what is then used by producer and consumer, right? To store and eventually, pull data out of these, out of Kafka logs. So in a way, this has, again, a hub and spokes, quote unquote, centralized architecture, centralized because, this broker have to be, this set of brokers have to be deployed in a data center, and we need to know where the data center is. And in this case, we only support pull mode. So you see that, I mean, individually, there are technology that solve very well a specific problem. They were designed for a given problem at a point in time, but the problem that we are trying to solve today is different, because today we have more and more systems, once again, that span from the data center down to the microcontroller, and we have very articulate communication pattern that we need to support. And so the situation was really messy, okay? And for me, it was very frustrating. And those of you that are familiar with the sort of things I did in the past, was very frustrating because I was, pointing this out, but again, I was a minority voice, okay? And everyone was either ignoring the problem or pushing the technology they adopted, or were selling, or just, just thinking that the problem wasn't there. But we couldn't. And, in spite of people thinking that we were kind of out of our mind, we decided to undergo a new beginning, because that's really what was needed. And so we decided to take the challenge and design a new protocol, a protocol that could work in the cloud to device continuum, a protocol that would leverage all the experience that we have had, in 20 years of distributed system. And again, today we have experience with building air traffic control systems. We are deployed in a NASA space launch system. I could continue for hours. Fujitsu, the Onefinity switches, they run on our technology also. So we have been working on super complex system. We know the challenge that typically appears, and we knew, where things kind of got complicated, and had an idea of what we had to do differently. And so we said, yeah, let's give it a try, okay? And this is what we did. And besides the problem of making sure that we could have data in motion, so data moving without barrier, unconstrained, as in our mission, from the data center down to the microcontroller, the other big problem that we were facing, and our users were facing, is that when you use a publish subscribe, you enjoy a property that is called location transparency. What is location transparency? Location transparency makes sure that as a subscriber, I express the data I'm interested in, and then it is the communication stack that delivers me the data without me having to know where the data is coming from, okay? So I don't need, it's not host-centric. I declare the interest on a topic, on a subject, on a resource, whatever. Don't care where is the producer, I get the data. As soon as you store the data in a database, you lose location transparency. Because if I store data in a database, then in order to retrieve this data, I need to know where the database is running. So I go back to an host-centric model. And this works very well if you have one database or one data storage technology deployed in a data center. But what if I have the need to decentralize the storages? How do I keep track of where the data is? It gets very complicated. How do I issue a query? I mean, it gets super complicated. And we really wanted to solve also this problem because it was a big pain. And so that was another element that we added into the challenges that we wanted to address in Zenoh. And so the result was Zenoh, also known as the Zero Network Overhead Protocol. And Zenoh, in fact, is a PubSub query protocol. So it supports the three things. And we will see that, actually, it provides universal abstraction. I'll explain why. I mean, we'll get there. But we were able, in the design of Zenoh, and by the way, it took us a few iterations, right? Because there is no magic wand. You have an idea, and then, you do it the first time, you look at it and says, that could be improved. So I think it was at the third iteration that we really came up with a minimal set of abstractions, as we will see soon. But so Zenoh is a PubSub query protocol that unifies data in motion, data at rest, and computation, as we will see, from the embedded microcontroller up to the data center. And again, you get location transparency both for data in motion, so for PubSub, as well as for distributed queries. That means that you can issue a query, okay, in a query language, and you don't need to know where the databases are, which is great. Zenoh, as we will see, figure out where is the optimal place to go and fetch the data, okay? Which is precisely what you would want to do in order to be able to build systems that scale. So in other terms, today, if you think about your smart meter at home, it's storing data in the cloud. If you are at home and you need to retrieve the data, you have to go to the cloud. Waste of energy, waste of bandwidth, and with Zenoh, potentially you could decide to store all the data at home, or to store part of the data at home, part of the data in the cloud, and depending where you are, if you are at home, you issue a given query, as you will see, you get it from the storage that is at home. If you are traveling, you're on the other side of the world, depending on where you are and what is closer, if it's the cloud or one of the cloud where the storage is, or your house, you get the data from the closest place. But again, we'll get to understanding how that does. Okay. And I love this quote because I think that this really, summarizes what we went through and what we are still going through. So make this quote yours, and Yeah. Okay, so getting back to Zenoh. Zenoh is PubSub, so but not only. Again, you can have a publisher or a peer that publishes some data, and a subscriber that is interested in receiving that data, so that resource that will receive. So this subscriber can be push or can be pull. And and you decide what you are when you declare your subscription. Again, pull subscription are super important for devices that undergo duty cycle. So that way we can support both devices that want to be triggered as soon as there is new data published somewhere on the network, as well as devices that are under duty cycle, and they decide when eventually recover data that was published. From where do they get this data? It depends. And as we will see, in general, Zenoh is smart enough to cache this data in the closest infrastructural node to the pulling subscriber. So again, for traditional publish subscribe, we support push and pull. But we support also a pub store get. So publication, if there are storages, as we will see, whose key expression matches the resource that you are publishing, these storages will store this data, and eventually, somewhere on the network, you can issue a query that will retrieve this data. And again, where this data is retrieved, you don't need to know. You see that you are querying, and we will see the query syntax. You're querying a set of data. You are not querying a location. Okay, you don't need to know where the data storage is. And as we will see, with the same mechanism too many clicks. Apologies for that. Let me go again through the animation. So what I was saying is that with the same primitive that we use for, then this is really bothering me. Okay. So this 3 times luck, hopefully. Okay, with the same technology that we use for querying, as we will see, that can also use to represent distributed computation. And it's exactly the same abstraction. So in short, you can do PubSub, push and pull. You can have, publish, store, get. So you completely decouple the publisher and the consumer can have arbitrary query across multiple resources and so on and so forth. And some of the primitives that allow us to implement storages along with the queries can also be used to represent distributed computation. And the other nice things, as we will see, as you always reason about resources and query on these resources, all of a sudden, you have complete transparency on whether some information that you are receiving, you are getting it because it triggered a computation or it triggered a database lookup. And that's good, because sometimes you want to change and take compromise between storing data versus recomputing, and so on and so forth. And this makes it quite powerful. So Zenoh also works essentially across any kind of topology. So in Zenoh, we support peer-to-peer. And by the way, most of the technology that claim to support peer-to-peer, they support a specific case of peer-to-peer topology, which is the click. So the case in which every peer has direct connectivity to every other peer, either because of leveraging some multicast transport, like UDP multicast, or because having a point-to-point connection to every other peer. So DDS, for instance, assumes that you have a click connectivity. But in Zenoh, we can support click, but we can also have peers over an arbitrary mesh. So as far as you have a connected graph between the peers, we are able to route communication. And this is very powerful, especially suppose you have a platooning application of robots. You are in an area, robots could be agricultural machinery, whatever, cars. They are platooning, and they don't have direct connectivity to each other. So if the first, let's say, tractor needs to exchange data with the last tractor, they cannot talk directly. So how do they do? Well, in that case, it's Zenoh that meshes it up and does this routing. There is, for instance, a new standard called Brittlemouth for oceanographic exploration drones that has adopted Zenoh. And they have precisely this case of meshes made either by OpenThreadX or a combination of OpenThreadX and some serial. Again, in that case, you can assume a click, but you would have a mesh, but Zenoh can deal with it. Then you can have broker communication. And you saw that even in MQTT, you have just a client, broker, client, which Zenoh can support. But that's actually not enough, because sometimes there is no broker, there is no router. And let me give you an example. We have some application, again, for oceanographic use cases, in which you have a bunch of drones that are making some oceanographic measurement that are relatively powerful and can exchange data through communicating peer-to-peer, perhaps, let's say, over a click or over a mesh. But then you have some even more constrained robots that cannot afford to route data. And so in this case, for them, it's sufficient to pair up with the closest peer, and then it's the peer that will be able to broker communication between client and perhaps between this client and other peers. So super powerful, but again, this is not something that we put just because it felt cool. There are actual use cases in today's application that this kind of support are much more easy to write. And the other nice things is that in Zenoh, all of this is quite easy or transparent to set up. But that's not all, because obviously you can have routed communication, so router can route client, and for those of you that are advanced in the use of Zenoh, you know that you can deploy your own router infrastructure and use it to route data, perhaps across the entire globe. And so in this picture, you could think that perhaps the two, the mesh on the right and the click of peers on the left could be some applications So if to make things real, could be some tractors or some oceanographic drones that are produced by the same manufacturer, and then the client potentially could be some operator or some application that do some analytics from the other side of the world. And again, the other nice things is that if you have the farmer that is on the field, all of a sudden he doesn't need to control or to get information to the tractor through the internet. He can pair up and communicate directly, and depending on the capacity of his hardware, he can do that by either being a peer or being a client. And the big difference between peer and client is that a peer can route communication for other peers and also for other clients, and a client can't. So the client implementation obviously can be far more compact. Okay, let's look now into how Zenoh sits on the networking stack. So another decision, very cautious decision that we took, was to be able to have a protocol that could run on top of a data link. So if you recall the ISO OSI reference model, well, obviously here I'm not reporting on all the levels. I'm stopping at the transport level, just because this is typically what we use today in IP networks. But what this slide says and what this diagram says is that Zenoh can run on top of a serial link. Zenoh can run on top of plain Ethernet, and so on and so forth. And why did we do that? Well, we did that because in some situation, if you require IP, I mean, not even UDP or TCP, I mean, just the fact of having IP, that takes too much bandwidth. If your MTU is very small, right, or if you have a super constrained network, any layer you add takes bandwidth. And so we want to be able to remove that. So the consequence of that is that you can run Zenoh on top of the data link. And by the way, it's super simple to write transport plugin for your favorite data link or network or transport protocol. Then we can route between different networks. So all of a sudden, I can have application running on serial, other application running on Bluetooth, other on OpenThreadX, other running on a 10 gigabit network, on plain Ethernet, other on 10 gigabit on IP or TCP or UDP, whatever. And all of this can be mashed up together and use Zenoh end-to-end without having to bother where you're sitting, because the abstraction that you have is unified, and you're able, while using Zenoh, to sit at the right level on the network stack and minimize overhead throughout the entire network. I don't know any other COTS technology that supports this, and for sure MQTT doesn't, Kafka doesn't, DDS doesn't. And again, the reason why we did was to minimize network bandwidth and maximize performance. Zenoh is written in Rust for safety and performance, and I will go back in a moment to that. We have native API bindings, obviously, for many programming languages besides Rust, including C++, Python. You can do anything in Zenoh with Rest, and Julian will demonstrate quite a few demos of that. As we saw before, as I mentioned before, it is available on embedded and extremely constrained devices and networks, and our minimal byte overhead, wire overhead is 5 bytes. And so let me give you some more details on that. Something that in the early days of the protocol we were debating was, what is the right sequence number for Zenoh? And I mean, again, recall that we were trying to design a protocol that could run very well on a constrained network, where sometimes you have MTU of 127 bytes. There are some cases where BLE, where the MTU is 20 bytes and you cannot negotiate a bigger MTU. And so suppose you have a 20 bytes MTU and you are saying, well, I have a sequence number of 4 bytes. Well, you are taking a lot already only for the sequence number. And you really don't need that big sequence number. And so you could say, okay, fine, I will have a sequence number of 1 byte. But then if you do that, if you are communicating over a satellite link, that doesn't work. Why? Because in a satellite link, to maximize the bandwidth, you want to have lots of packets in flight, and you have to make sure that your sequence number resolution is big enough that you avoid the rollover. And so what we did in Zenoh, among other things, and this is why one of the reasons why we can really push the wire overhead to 5 bytes, and by the way, 5 bytes, assuming you send data sporadically, because if you send data frequently enough, that 5 bytes becomes even less, okay? It will tend eventually to roughly 2 bytes, okay, 2 to 3 bytes. But going back to the sequence number, what we did was to allow sequence number resolution to be negotiated when you establish a session, which is what makes sense, right? Because if I'm a device on a low power network, and I probably want to use a sequence number that has a very small resolution, 7-bit might be enough, okay? And that's what I should use. Why should I be forced to use the same sequence number resolution that is used by an application that communicates over a 100 gigabit network? Doesn't really make sense. And so the point that we want to make is that you don't need new protocol for all of those cases. You just need a protocol that is properly designed. And this is what we try to do. So getting back to Rust, why Rust? Well, now Rust is no more something for weirdos. And by the way, it's a super cool language, and it's getting, it's growing very fast for good reasons. But I mean, for those of you that don't know, the very first version of Zenoh was actually written in OCaml. And many of you will say, oh, what? OCaml is a functional programming language, actually a quite nice programming language. And the reason for us to write it in OCaml was first of all, well, because you get pretty good performance. I mean, we could have performance for the core of Zenoh that were pretty close to C. But the other reason was that security was super important for us. And again, when you use a programming language that is safe, you are cutting out an entire class of bugs that then can bite you back with respect to security. And there have been quite a few reports, the latest one from the NSA, the National Security Agency. This came out, I think, last week or maybe 2 weeks ago. You get the link as part of the image. That once again was recalling 70% of the security vulnerability are due to memory safety issues. And so when we decided to open source and we wrote the latest iteration of Zenoh in Rust, we wanted really to have a memory safe language. OCaml wasn't anymore a choice for us because we had some user complaining that it was very hard to understand the code base, it was very hard to find OCaml programmers. And so in the end, we reevaluated Rust, which, by the way, with the 2018 edition was now, from our perspective, a very usable programming language. And we re-implemented Zenoh in Rust, and we're super happy about it. And with that, we enjoy, great performance, memory safety, concurrency safety, and the productivity compared to C++. I mean, it's night and day. We've done lots in C and C++. We still have some product developed in C, so we can make those difference and those analyses quite easily. Okay, real quickly on these slides, as I mentioned before, you can have Zenoh running on your favorite MCU. And let's move to abstractions. So in terms of abstraction, Zenoh deals with resources. What is a resource? A resource is named data. In other terms, it's a key and a value. So as example, I might have a sensor in my room and in my kitchen, and I could give it a name like ohm/kitchen/sensor/temp. And at some point in time, it would have the value 21.5 degrees Celsius. Okay? So this is what Zenoh deals with. Think of Zenoh as dealing with abstract things that are resources, and resources have a name and a value. Then the name of this resource, we typically call it a key. And it's structured as you see here. And this is convenient because then you can have key expression. A key expression is a way of identifying a set of keys, and as a consequence, denoting a set of resources. So for instance, if I'm interested in all the sensors in my kitchen, well, those are ohm/kitchen/sensor/star. If I'm interested in all the temperature sensor across all the rooms in my house, that would be ohm**temp, because ** expands to any level of nesting. Again, key expression is a way of selecting a set of keys and thus denoting a set of resources. Then we have a selector. What is a selector? A selector is an expression identifying a set of resources satisfying a given predicate, okay? And also allows to do interesting things like projections. So here, in this example, you see that I have home/star/sensor R. So for across all my rooms, I'm interested in the air sensor, but you see there is the question mark only if the CO2 attribute of the air sensor is greater than 12, and in that case, the only things that I'm caring so that I want projected is the humidity. Isn't that cool? Okay. From what kind of database am I going to get this? I shouldn't know. Is it a MySQL? Is it a RocksDB? Is it an InfluxDB? Who cares? Okay. You have an abstract syntax to query databases. You don't know where they are, right? You get location transparency, uniform way of accessing different storage technology, because this could be stored on a file system or in memory. You really shouldn't care, okay? And that gives you the ability of changing the storage technology over time. And by the way, this is the syntax that Zenoh supports off the shelf with a storage plugin that we provide. The other important things to understand is that the actual query language, okay, is understood by the storages. So we came up with a query language that you can use with the storage we provide. But if you don't like it, and you suppose you say, hey, I want to use SQL, okay, but you write your storage plugin and you use SQL, because Zenoh uses the key expression to route the query, and then it triggers the query on the plugin for the storage or the queryable, which is executing it, as we will see, and returning the relevant data that then Zenoh routes back. So let's continue with abstractions. In Zenoh, we have a publisher, which is a string of value for a key expression. So in this case, you see a publisher could say that, hey, I'm publishing data for the resource named home, kitchen, sensor, temp, or I'm publishing data for all the sensors in the kitchen. Then you have a subscriber, which you can visualize as a sink of value for a given key expression. So again, I'm interested in receiving data for home, kitchen, sensor, temp, or you put a wildcard, it would be all the sensor in my kitchen. And then we have a queryable. A queryable, it's something that perhaps you have never met before. A queryable, think of it as an oracle that answers queries whose key set match the queryable expression. So for instance, I can say, hey, I'm a queryable for the key expression home star. That is a promise that if you issue any query on the resource set whose keys matches or is matched by home star, then I promise that I have something to say, okay? How do I have something to say? Well, you shouldn't know, right? That's a matter of implementation. And so in a way, right, we have three network endpoints. You have publisher, which produce data, subscriber that does plain sync, and then there are queryable. You have to visualize them as this entity across the network that says, hey, you're looking for data that matches this key expression, just come to me, okay? So I think you're starting now to get the idea on how things build up in Zenoh. And so why do we typically say that Zenoh abstractions are universal? Well, they are universal because they allow you to express the key patterns in distributed computing natively, right? I mean, think about other technology. If we take the example of DDS, DDS is a PubSub, and then on top of this PubSub, there is an RPC, and the two fight with each other because, I mean, the model is completely different, and you're trying to build now host centricity out of something that is location transparent. So, but Zenoh managed to give you that model of, service invocation across the network without having to introduce a location dependency. But getting back to the Zenoh abstraction universality. So in Zenoh, you have publish subscribe, that's trivially supported by Zenoh publish and subscriber. You have remote computation, right? Because a queryable can be used to represent a generalized computation, since it can be, transparently deal with replication and partitioning based on how you select how you submit your query. But you will discover this in the next episode. And then you can represent storages, because what is a storage in Zenoh? A storage in Zenoh is nothing but a combination of a queryable and a subscriber. Why? Because the subscriber is the part that essentially you use to write on the storage, and the queryable is the reading half of the storage. Okay, so this is really how on the network a storage, when you activate a Zenoh storage, is advertised, is nothing but the combination of a queryable and a subscriber. So again, you have support for PubSub, push and pull. You have support for remote computation with Queryable. And by the way, in the next release, finally, we are also attaching or adding attachment or body to queries, which is quite useful. Because before you had to pass everything on the on the query. And you have storages as a combination of Queryable and subscriber. Okay, and all of this primitive, all of this abstraction enjoy location transparency. So let's visualize this in action. So imagine that this is my system. I have a bunch of robots. And again, I mean, I use robots just because this is something easy to play around. I mean, we have those everywhere, but this could be anything, right? It's just to have something that you can relate with. So in this case, potentially one robot is publishing some data, and you see that it's publishing its position. So it's in fleet 1, robot 2, it's publishing position. The storage on the upright corner had a key expression that was matching this key, so it's stored, and the subscriber also received that data. There is another robot around publishing its position, and now you see that depending on the matching key expression, the data is automatically delivered to the subscriber and the storage. But notice what happened. Actually, the data was also cached in a router for the subscriber that was on pull mode, and whenever he woke up, he managed to retrieve this data and consume it at its space. And again, when you're a pull subscriber, whenever you pull, you can decide how much data you want to pull. And then will garbage collect the data that is cached throughout the network only once you have consumed all the data that was for you. Okay, now suppose that we wanted to issue a query. So some application comes later and says, hey, hold on a moment. I would like to know the position for all the robots in my fleet. And in this case, he sees, right, that based on the key expression of the storage and the queryable that exist, he has to interrogate these three queryable in order to get an answer. And in general, I mean, I don't want to bore you, but technically, whenever you submit a query, what Zenoh does, it performs a set cover. It says, okay, this is the set that you're interested in. I know the queryable that are around. What is the minimal set of queryable that is the closest to me that actually can cover, and I mean a set cover operation, your query. And once he realizes that, then it routes the query, the execution of the query is triggered, and then by using a mechanism such as breadcrumbs, routes back the result, consolidate the result, and you get the result without knowing where the data is stored. Okay, in terms of primitive, obviously we have open and close, and well, you have pluggable authentication, so on and so forth, and a typical declaration, but you will have all the details in the next episodes. And then I just want to get here, because the primitive, really, to operate with Zenoh, are put, pull, and get. Okay, and obviously there's the subscribe to get the subscription. But the API, it's so simple and elegant, and I hope you appreciate that, because, you know, we put a lots of effort in trying to give you a clean API, and an API that gives you a promise, okay? Well, as no accidental complexity, and we work very hard on that, and performance transparency, meaning please look at our performance test, the one that we use to publish the performance result. There is no strange code. It is precisely the same code that we teach you to write in our tutorial. So you don't need to play any strange trick or write code that is hard to understand or to maintain. You write regular Zenoh code and you get the performance that you advertise. And this is super important because, I mean, you shouldn't do contortioning to get performance, right? Performance should come from a good implementation, which is what we do. So Zenoh is extensible. We have a bunch of plugins. Again, we will have a full webcast covering on this. But what this already tells you, I have a robot that is using ROS with DDS, and I want to do robot-to-robot communication, and I've trouble with DDS because it doesn't work well on Wi-Fi. Well, I can use Zenoh, and you know that is used quite often in robotics to solve that problem. I have MQTT, and I want to leverage some Zenoh. We have a plugin for that. I like the storage concept. You know, we have today's plugin for InfluxDB, RocksDB, MariaDB, file system, Amazon S3 is coming up in the next release, and so on and so forth. So how does Zenoh perform compared to the other technology? And again, here we have some example compared to MQTT and Kafka. And you have the difference in green is Zenoh routed, so peer, router peer, and in violet is peer-to-peer Zenoh, while in blue you have Kafka, and in red you have MQTT. And you see that Zenoh just blows away the other technology in terms of performance, with respect to throughput and with respect to latency. Because, I mean, throughput here, we peak at 60 gigabyte per second, right? And you're seeing that MQTT is peaking 8 gigabyte and Kafka at 5, right? And in terms of latency, Zenoh has a latency of 10 microseconds compared to 25 microseconds MQTT and 75 for Kafka, okay? And if you think about how you can have this query that are executed on distributed storages, you can think of Zenoh as a Kafka for edge computing, or at least this is one of the use cases. If we look at another dimension, which is not raw performance, but wire efficiency, one of the dimensions that is very important is that discovery data. For instance, one of the challenges that DDS has when running on wireless network is the amount of discovery that it creates. This is an evaluation done from Open Robotics. The full report is quite interesting. I've put the link here. But it shows, in blue, you see the difference between the amount of discovery data that there is in Zenoh versus DDS. And on scenario 1, you can see that in DDS, I mean, you're essentially communicating just discovery data and very little data, because this is a ratio. And again, I suggest that you look into that report, because it's very insightful in understanding some of the tricks that Zenoh plays and the performance that you get out of it. Then if we look at the feature matrix, again, summarizing a little bit what we've seen, PubSub, you have push and pull in Zenoh, but many of the other technology either support push or pull, not both. Distributed queries, Zenoh is the only one that supports. High performance, well, DDS is quite high performance. Zenoh is very high performance. Typically, throughput is higher than anything else you have in this table. Constrained hardware. Well, you can get MQTT on constrained hardware. You cannot get it on constrained network unless you are okay to use TCP/IP, which usually is not the case. And that's not a problem with Zenoh, because we have seen we can even sit as low as data link. Internet-scale deployment, obviously, that's where DDS suffers and the other are better off. Standard-based. Well, DDS and Kafka are not standard-based, but Zenoh is open source, and Zenoh is part of Eclipse, so it's an Eclipse project, so there is a fully transparent and well-defined governance. I think this matters more than anything, because open source, I mean, I've been in standard for a long time, and there is too much politics. It gets too slow, and in the end, it don't always operate in the interest of users, but end up being just a lobby of vendors. And this is not what we want to have with Zenoh. QoS, obviously, there is some support for QoS in most of this technology. Peer-to-peer is just DDS and Zenoh, not the others. Brokered is not DDS, is the others. And routed, you see, it's only Zenoh, whose protocol is also able to route. Let's go real quickly to some examples, shiny, happy users. So we have application today in several domains. Here I'm showing some example in autonomous trains, race cars, robots, but we have application also in high-performance computing, in industrial automations, and so on and so forth. Actually, it's good to see some of the things in action. And by the way, you will learn more on how these things were achieved. In the autonomous train that you are seeing, Zenoh is used both on board for driving the train as well as the train to infrastructure communication. User love it, right? Again, if you like Zenoh, give us a star. Join our Discord. On Discord, I mean, thank you, to our user for sharing their success, but I mean, they're enjoying incredible performance improvement. Here you see an example about, 20 to 60% performance improvement over gRPC in some cases, in other cases 10 to 5, I mean, which is incredible. Other application in industrial automation from Flex, and everything working great. So, we are very happy to support you guys, and please share your success story as much as you share your problem, because that's the way in which we can improve our product. Strong endorsement. So the Open Foundation is looking to have a Zenoh-based, native Zenoh-based support for the robot operating system, and that's as a result of the evaluation that they did a couple of months ago. Recently, there was an ITU recommendation of making a standard for intelligent transport system based on Zenoh. So this would mean that cars and roadside infrastructure would eventually communicate using Zenoh. And there was a very fascinating use case on digital witness that we demonstrate how easy it was to solve through geo-distributed Zenoh queries. So coming up and trying to wrap up. So Zenoh is probably the most wire and power efficient protocol on the market. Okay, it provides, again, connectivity from the microcontroller up to the data center. As we saw, support push as well as pull PubSub and distributed queries. Resource keys, because maybe this is one of the questions that you have, go on the wire typically only at declaration time, unless those are pre-declared and they're represented as integer. And this representation is automatic, so you don't need to deal with integer assignment anywhere in our application, because that doesn't scale, that's not possible. As you saw, we have peer-to-peer and routed communication, as well as client-to-peer or client-to-broker. We have support for zero copy. That's very important when you're running on the same memory domain and want to completely avoid the network stack. And so, concluding, right, Zenoh, as I hope you are starting to appreciate, has been designed to overcome the limitation of existing protocols. And besides the technical limitation, in the given problem domain, there was another gap, which was unification of data in motion and data at rest. And this is also what we've done. And we've managed to do that, from the data center down to the microcontroller. And our commitment is to make, this protocol, which we think it's quite hot, more and more supportive with respect to the advanced use case that contemporary applications have to deal with. It's written in Rust for security and performance. It has a very vibrant and quickly growing community and impressive performance. So if you want to learn more, obviously you can join our Discord. So you have an invite precisely on the link of the image. You can get it out of our GitHub, and you'll find more and more documentation, because this is one area where we have to have continuous improvement on our website. And again, if you loved it, please give us a star on our repository. So thank you for your attention. I will be stepping out presentation mode. If there are questions, please write those on the chat, and I'll be answering them in order. Any question that we wouldn't be able to answer because of time, then we will post answer to all the questions that we got. Okay, so there is a question from Jan asking, what are the QoS in Zenoh? Okay, so first of all, there are QoS to control network traffic prioritization. Okay, so we can have end-to-end priority, and that impacts scheduling. There are QoS controlling reliability. There are QoS controlling what you do in congestion control. Okay, and there are, by the way, some mapping, because some people, especially people that are familiar with DDS, they think that in DDS you have lots of things that the communication stack, like it enforces deadline. Well, deadline are just a local trigger. Okay, deadline in DDS don't do anything. So if you think about DDS QoS, you typically have the equivalent in Zenoh, and if they are not there, it's because we think that in a modern programming language, implementing some of those quote-unquote QoS is pretty straightforward. But the fundamental for traffic prioritization, reliability, and congestion control are in place. Okay. There is another question asking if Zenoh can be used in Ethercat. Yes, you would have to write a transport plugin. So we have not tried that yet. It would be an interesting exercise. So, I mean, don't hesitate to post any question on Discord if you have. Okay, so there is another question. Let me read if we have. Okay, Tanisha, I'm not sure I understand your question, but let me try to rephrase. I think your question is if you have something. Okay, I think you have you are producing a time series, so you are producing something that so evaluate over time, and then in that case you can express a regular subscription to receive it. If you have a pool subscriber, as a pool subscriber, you will still get all the samples, and then where things get interesting is with queries, okay? So if I have, again, a sample that is written over time, so I have a time series, depending on the storage that I have in my system, I will be able to retrieve the history, so the time series, and query the time series if I have time series database on somewhere on the system, okay? Otherwise, no, the querying over time is supported by Zenoh, but the answer that you get really depends on the database that you have configured on the network. So in that case, you would really need a time series database like InfluxDB, which we support. So there is another question. Okay, so if there is a developer guide available or planned. So we are working on a Zenoh book, meaning a cargo book, which should be out with the next release. The best place to start is really the, actually, let me share on my screen, because the API, it's honestly quite simple. And as we have, so if you go on the Zenoh.io, the best way to start really is the documentation. And you will, in the code, the other nice things is that you start with the language, and then we have made sure that we have examples that are exactly the same for all programming languages. So if I go on GitHub, so if I take the examples here, okay, you will see that you have a given list of examples. If you go in Python and other programming, C or C++, you will find exactly the same example. So we typically on our website explain in Python, but then you have references to other examples in other programming language, which mirror. So once you understand the principle, you learn in one programming language, and then it's like a Rosetta Stone, right? I have exactly the same example in all programming languages. But again, a cargo book is coming. We're investing more effort on the documentation. And one of the reasons for having this webinar series was to make sure that we can fill some gap, and so provide you open and free in-depth training that then will be available also offline that you can get to. But of course, a documentation that you can have offline and on your desk or at on your browser is useful, and we're working on that. Okay, other question from, and good feedback from Satyam. So API seems very straightforward. It is. The configuration seems difficult to understand. So there is some information, and we'll make an additional effort to clarify that. And by the way, this is perhaps a good idea for an additional webinar or section on one of the webinar on configuration. Because we provide, once you understand how it works, it's pretty straightforward, okay? And perhaps there isn't sufficient documentation. This is something that we have improved since the last release, but again, we'll do more. And don't hesitate to ask questions on Discord. Let me still browse through the questions. So there is another question concerning the security model. So in Zenoh, as of today, you have pluggable authentication, and off the shelf, you can authenticate through X509 certificate using TLS, or you can authenticate through user ID and password, or combine the two, and you can chain authentication. The session opening doesn't retain any state, which is very important to avoid denial of service attack. And the only catch, well, two things for you to know, that as of today, authentication is only on the infrastructural nodes. With the next release, which is forecasted for mid-December, you will have mutual authentication, at least for TLS. I think I answered the bulk of the questions. So once again, I would like to thank all of you for joining us today. See you in our upcoming webinar. The next one will really go deeply into how to get started with Zenoh. And again, based on the feedback that we had here, I will ask Luca also to cover some aspect of configuration. So definitely, you will get some information then in the next webinar. And as I said, we're working on a cargo book for Zenoh, so that will be, again, a big step forward, making the technology simpler. Okay, there are still lots of questions. Okay, so is there a white paper or documentation about how Zenoh work? If you mean about the protocol, we used to have a spec of the protocol, okay? There were a few changes that we did on the protocol, and we decided to retire that document. So as of today, the code is very well documented, but there is no spec of the protocol. This is on our to-do list. But again, if you really want to understand how the protocol works, you should look at the code. And recall that we have two implementations of the protocol, one in Rust, and the Zenoh Pico, which is what we use on microcontroller, actually is written in C. And we are working on seeing if we can use, again, some of the latest development in Rust also to have a pure Rust implementation on for Pico. But anyway, the point is that there are two independent implementation of the protocol, which is for us very important, because the team working on Zenoh and Zenoh Pico are different. So that ensures interoperability, ensures that the protocol is easy to understand. The protocol is I think, well structured. But indeed, a specification, an open document will eventually come. Okay. Okay. So, well, thank you for the, for sharing, your liking of Zenoh. So very, very happy of that. We put all of our passion and all of our skill into that. And, it's good to see that you guys are enjoying. So we will keep doing more of it. And thank you. So I look forward to seeing you on our upcoming webinar. Thank you very much. Ciao, ciao.